Hello everyone, my name is Kylie de MONSERRAT and today I will be presenting a comprehensive look at AAMT 2206, Aircraft Weight and Balance. We will explore the technical fundamentals and walk through a practical problem-solving scenario. Our goals for this session are to define key terminologies and formulas, interpret and apply Type Certificate Datasheet or TCDS information, calculate empty weight center of gravity or EWCG, loaded CG and percent Mach, evaluate whether an aircraft is within the safety limits and applies necessary CG corrections. Weight and balance are critical factors in aircraft design, performance, and stability. We must manage weight in two ways: absolute, which is the maximum structural load, and relative, which refers to how that weight is distributed according to the flight manual. Before we calculate, we must understand the references. Datum, the starting 0 point for all measurements, often located at the aircraft nose or wing leading edge. Arm, the horizontal distance from the datum to an item's location, measured in inches. It is designated as positive or negative based on its positive relative to the datum. Center of gravity, or CG. This is the specific point where the aircraft's total weight is concentrated. We find it by dividing the sum of moment by the sum of weight. Moment. This is the rotational force created by weight. It is calculated as weight times arm. Empty weight CG or EWCG includes the airframe, engines, fixed equipment, and unusable fluids. Loaded CG. This is the actual position once we add the variables for crew, fuel, cargo, and passengers. To understand stability, we use Mach, the average width of the wing. We measure from the leading edge, Mach, to the trailing edge, Mach. By calculating percent Mach, we can express the CG position as a percentage, which tells us exactly how stable the aircraft is relative to its wing. If the CG is out of range, we use weight shifting. By moving a load a certain distance, we change the CG position. The formula used is delta CG, or is equal to the distance moved times the ratio of shifted weight over total weight. CG correction. This is the process of adjusting the aircraft's load by shifting or removing weight to move the center of gravity into the required safety zone. And the final CG, this is the confirmed balance point after all adjustments are made. It must fall within the manufacturer's allowable limits to ensure the aircraft is safe for flight. With the terminologies and formulas covered, let's apply them to a practical scenario using the TCDS and tabulated data. We'll begin with the sample problem. The aircraft is weighed with full operating fluids and unusable fuel. The scale readings are nose gear at 9,450 pounds at 92 inches arm. Main gear combined 27,100 pounds at 325 arm. The aircraft is prepared for flight with a minimum required crew consisting of a pilot and co-pilot with a combined weight of 370 pounds. Fuel on board consists of forward tank 320 gallons, center tank 410 gallons, rear tanks 210 gallons. Fuel weighs 6 pounds per gallon. Oil on board is 66 gallon, weighing 7.5 pounds per gallon. Cargo is loaded as follows. Compartment C is 3,100 pounds. Compartment F is 3,600 pounds. Compartment H is 4,100 pounds. Use the midpoint of each compartment range for arm determination. From the TCDS, we will obtain the essential data needed for the computation, including the arm, Mach, Mach, and the allowable CG limits in percent Mach. These values allow us to convert the center of gravity from inches to percent Mach and determine whether the aircraft is within safe operating limits. Moving on to the problem solving, in this part, we will apply the concepts by organizing the given values into a table of weight, arm, and moment. To compute for the EWCG, we first list all the scale readings along with their corresponding weight and arm. For the nose gear, we have 9,450 pounds and 92 inches for arm, while for the main gear, combined, we have 27,100 pounds and 325 inch in arm. Next, we will multiply each weight by its arm to get the moments. So, 9,450 times 92 is equals to 800,069 and 400. And next is 27,100 times 325 equals to 8,807,500. We then get the sum of all weights and the sum of all moments. Now, 9,450 plus 27,100 is equals to 36,550. Next, 800,069 and 400 plus 8,807,500 is equals to 9,676,900 pounds inches. Finally, using the formula for EWCG, we divide the total moment by the total weight. So now, 9,676,900 inches divided by 36,550. We will cancel out the pounds. Now our EWCG is 264.7578659 inches. We will only use the rounded off 2 decimal points for the final answer, so 264.76 inches. Now that we already have the EWCG, we will now proceed to solve the loaded CG and percent Mach. We will make a table. First, we will write the given items. We have empty aircraft, crew, pilot and co-pilot, fuel forward tanks, fuel center tanks, fuel rear tanks, oil, cargo compartment C, cargo compartment F, and cargo compartment H. Second, we will get the weight for the empty aircraft. Its weight is 36,550 pounds, which is the sum of the weights of nose gear and main gear combined. The crew, pilot, and co-pilot combined weights 370 pounds. For the fuel, we will multiply each by 6 since it is stated in the problem that fuel weighs 6 pounds per gallon. For the forward tanks, 320 gallons. 6 is equals to 1,120 pounds. For the center tanks, 410 gallons. 6 is equals to 2,460 pounds. And for the rear tanks, 210 gallons, 6 is equals to 1,260 pounds. The oil on board is 66 gallons, weighing 7.5 pounds per gallon. 66 is multiplied by 7.5 is 495 pounds. Lastly, we have 3,100 pounds for cargo compartment C, 3,600 pounds for cargo compartment F, and 4,100 pounds for cargo compartment H. Third, we will get their arm. Referring to the TCDS, for the empty aircraft, we will use the commutated EWCG. For the crew, we have 80-inch, 304-inch for forward tanks, 340-inch for center tanks, and 374-inch for rear tanks. Oil is in 253-inch. For the cargo, use the midpoint of each compartment range for arm determination. We will add and divide by 2. For cargo compartment C, 194 plus 276 is equals to 470 divided by 2 is 235-inch. For cargo compartment F, 358 plus 440 is equals to 798 divided by 2 is 399 inches. And for cargo compartment H, 440 plus 542.5 is equals to 982.5 divided by 2 is 491.25 inch. From there, we compute each moment by multiplying the weight by the arm. We now have all the weight, arm, and moment of each item. Next, we will get the sum of all weights and moments. Total weight is equals to 53,855 pounds. And total moment is equals to 15,902,158 lb inch. Here is the digitalized version of the table for better visualization. Now, we will solve for the loaded CG using its formula. Total loaded moment divided by total loaded weight, which is 15,902,158 divided by 53,855. Is equals to 295.2772816 inch or 295.28 inch, which is not within the range. Now, we will use the loaded CG to compute the percent Mach. Our formula is percent Mach is equals to loaded CG minus La Mach divided by Mach times 100. The La Mach and Mach are provided in the TCDS. So, 295.2772816 inches minus 275.61 divided by 164.25 times 100. Is equals to 11.2 97564688%, which is not within the range. The loaded CG must be 313.4 inches while the percent Mach must be 23% because our total weight is above 40,000 pounds. With this, we need to conduct weight shifting. First, we will compute for the change in CG 313.4 in which is stated in the TCDS for the range minus 295.2772816 in which is the computed loaded CG. Is equals to 18.1227184 inches. Second, we will compute for the distance weight is shifted. To get this, we need to move some weight to other cargo compartments. For this, we will utilize compartment C and the farthest compartment J. So, for the distance weight is shifted, we need the arm of compartment C and J. We already have the arm of compartment C. We only need to solve for the arm of compartment J. Based on the TCDS, 615 plus 74 is 1,319 divided by 2 is 659.5 inches. So, 659.5 minus 235 inches is 424.5 inches. Now that we already have the change in CG and the distance weight is shifted, we can now use the weight shifting formula. Weight shifted divided by the total weight and change of CG divided by the distance weight is shifted. But since we are looking for weight shifted, our formula will be weight shifted is equals to the total weight times change in CG divided by distance weight is shifted. So, 53,855 pounds times 18.1227184 inches divided by 424.5 inches. We need to cancel out the inches. And our weight shifted is 2,299.173144 pounds. With this, we will have a new cargo weight and moment for the two compartments. For compartment C, we will get the difference between its weight and the weight shifted to get the new weight. (3,100 minus 2,299.173144) is equals to 800.8268565 pounds. We will have the same arm 235 inches. Now, the new moment is 188,194.3113 pounds inches. For compartment J, we will use the weight shifted as its new weight. Its arm is 659.5 inches. Now its new moment is 1,516,204,688 lb inches. So we will now recompute the total moment since there are changes in the moment of compartment C and an additional moment of compartment J. Our new moment is 16,878,157 lb inches. As shown, the table has been updated to reflect the new weight and moment values for compartment C and J. We do not recompute the total weight because no weight is added or removed. Only its position is changed. Now that we are done with weight shifting and CG correction, we will now compute for the new loaded CG and new percent Mach and see if it's already within the range. Using the formula for loaded CG, total loaded moment divided by total loaded weight, £16,878,157 inches divided by 53,855 pounds is equals to 313.4 inches, which is now within the range. Now for the last part, let us see if the percent Mach is within the range using again its formula loaded CG minus the Mach divided by Mach times 100. So 313.4 minus 275.61 inches divided by 164.25 inches times 100. Is equals to 23%, which is also now within the range. And with that, our loaded CG and percent Mach are all now within the range. Here are the summarized computations. Initially, our calculations revealed that the aircraft was out of balance, posing a potential safety risk. However, by redistributing the load, we adjusted the total moment and brought the center of gravity back into the safe zone. This final configuration confirms that the aircraft is now properly balanced and ready for stable flight.